Cloud point phenomena in surfactant systems, fundamentals, mechanisms, and influencing factors. The cloud point is a defining characteristic of many surfactant systems, particularly non-ionic surfactants, representing the temperature at which phase separation occurs in aqueous solutions. This video provides an overview of cloud point phenomena in surfactants, emphasizing thermodynamic principles, micellar interactions, and the influence of molecular structure, concentration, and additives such as electrolytes. Differences between major surfactant classes are discussed, with particular attention to ethoxylated surfactants and emerging bio-based alternatives. The underlying mechanisms governing lower critical solution temperature, LCST, behavior are analyzed in terms of hydration, intermolecular forces, and entropy-driven effects. Surfactants are amphiphilic molecules that self-assemble into micelles in aqueous environments above a critical micelle concentration, CMC. Among their many physicochemical properties, the cloud point is particularly important for formulation science as it defines the temperature at which a homogeneous surfactant solution becomes turbid due to phase separation. The cloud point is most commonly observed in non-ionic surfactants, especially those containing polyethylene oxide, PEO, chains, such as fatty alcohol ethoxylates. It is associated with a lower critical solution temperature, LCST, above which the solution separates into two coexisting liquid phases. Definition and experimental determination of cloud point. The cloud point is defined as the temperature at which a clear surfactant solution becomes visibly turbid upon heating. This turbidity arises from the formation of surfactant-rich and surfactant-lean phases. Experimentally, the cloud point is typically determined by visual observation of turbidity, turbidimetry or light scattering methods, monitoring changes in transmittance with temperature. While widely used, the cloud point technique has inherent limitations: dependence on subjective visual detection, sensitivity to experimental conditions, for example, vessel geometry, illumination, influence of metastable states, and delayed phase separation. Thermodynamic basis of cloud point phenomena. Cloud point behavior is governed by the balance between surfactant water and surfactant-surfactant interactions. The phase separation observed at the cloud point corresponds to a transition from a single-phase micellar solution to a two-phase system. This behavior can be described using an interaction parameter, W, representing effective intermicellar interactions. At low temperatures, strong hydration of hydrophilic groups leads to repulsive interactions, stabilizing the solution. At elevated temperatures, dehydration of hydrophilic moieties reduces repulsion and enhances attractive interactions, van der Waals, and hydrophobic forces. When attractive interactions dominate, for example, the interaction parameter becomes negative, phase separation occurs, resulting in a cloud point. The process is largely entropy-driven, as dehydration releases structured water molecules into the bulk phase, increasing overall disorder. Molecular origin of LCST behavior. The LCST behavior of surfactant systems arises primarily from the temperature-dependent hydration of the hydrophilic head groups. Role of hydration. Hydrophilic segments, such as ethylene oxide EO chains or hydroxyl-rich groups, form structured hydration shells through hydrogen bonding. Increasing temperature disrupts these interactions, leading to reduced solubility, enhanced aggregation, and phase separation. Micellar growth and fluctuations. As temperature increases, micelles may grow in size, intermicellar attractions increase, and concentration fluctuations become more pronounced. Critical opalescence. However, cloud point behavior is not solely due to micelle size changes, but rather to collective interaction effects between micelles. Factors influencing cloud point. Surfactant structure. The cloud point is highly sensitive to surfactant molecular architecture. Hydrophobic chain length. Increasing alkyl chain length generally lowers the cloud point due to enhanced hydrophobic interactions. Hydrophilic group size. Increasing the length of EO chains or the number of hydroxyl groups raises the cloud point by enhancing hydration. Head group chemistry. Surfactants with strongly hydrated head groups, for example, sugar-based surfactants, may exhibit higher cloud points or suppressed phase separation. Surfactant concentration. Unlike many polymer systems, the cloud point of surfactants can show weak dependence on concentration in some systems, strong dependence on others, especially where co-observation occurs. Critical concentrations associated with phase separation are typically above the CMC. Electrolytes, salting in and salting out effects. Electrolytes significantly influence cloud point behavior. Salting out effect. Most inorganic salts reduce the cloud point by dehydrating the surfactant head groups. Salting in effect. Certain ions, for example, large, weakly hydrated anions, increase the cloud point by stabilizing hydration layers. These effects are often interpreted using the Hofmeister series, which ranks ions based on their ability to structure water. Electrolyte effects depend on ion type, cation versus anion, ionic strength, specific ion-surfactant interactions. Additives and mixed surfactant systems. Ionic surfactants. The addition of small amounts of ionic surfactants can significantly increase the cloud point by introducing electrostatic repulsion between micelles. Hydrotropes. Certain compounds enhance solubility and increase cloud point by disrupting hydrophobic interactions. Organic solvents. Co-solvents can either increase or decrease the cloud point depending on their polarity and interaction with water. Cloud point in different surfactant classes. Non-ionic surfactants. Non-ionic surfactants exhibit the most well-defined cloud point behavior due to the absence of strong electrostatic interactions. Ethoxylated surfactants are the classic examples. Ionic surfactants. Ionic surfactants typically do not exhibit cloud points under normal conditions due to strong electrostatic repulsion. However, in the presence of high electrolyte concentrations, LCST-like behavior can emerge. Polymeric and bio-based surfactants. Polymeric surfactants and bio-based surfactants may exhibit complex cloud point behavior, often influenced by molecular weight, functional group density, strong hydration effects. Practical implications and applications. Cloud point behavior is critical in various industrial and technological applications. Detergents and cleaning formulations determine performance at different temperatures. Emulsion stability. Phase separation near the cloud point can destabilize emulsions. Enhanced oil recovery. Cloud point manipulation is used to control surfactant partitioning. Separation processes. Cloud point extraction is used for the purification and concentration of solutes. In conclusions, the cloud point is a fundamental property of surfactant systems arising from temperature-dependent changes in hydration and intermolecular interactions. It reflects a delicate balance between enthalpic and entropic contributions, primarily governed by the dehydration of hydrophilic groups and the resulting increase in attractive forces between micelles. Surfactant structure, concentration, and the presence of additives, particularly electrolytes, play crucial roles in determining cloud point behavior. Understanding these factors is essential for the rational design of surfactant-based formulations and for controlling phase behavior in practical applications.